this is exploration number 1 on page 81 of your book, but it's a good problem involving a lot of different things on how to remove a discontinuity. So I have this function, and if I'm going to remove a discontinuity, I kind of got to see where it might be. So what I'm going to do is I'm going to graph it. Because before I graph it, I'm going to first do any kind of factoring that I possibly can. So I'm going to factor this. This is x cubed minus 7x minus 6. Now that numerator there, I do not know how to factor it. It is of the third degree. I can factor or use a quadratic equation for second degrees, and I can certainly solve first degree expressions. But a cubic, I can't do anything with it. But I also know my denominator is x plus 3, x minus 3. So my next step is to graph this. So I've entered it over here on the calculator in its original form, although it wouldn't make any difference if I entered it in the factored form of the denominator. And I'm going to graph it. So I'm going to go zoom 6. And I'm graphing it, and I see, well, I have a vertical asymptote. It looks like it's right here at -3, which doesn't surprise me because this is telling me I should have one undefined term at x equals -3, but I should also have another undefined term at x equals +3. Well, my graph over here at x equals +3, it doesn't look like there's anything there. I know there cannot be a point there. I know that it has to be a hole. There has to be a hole at x equals 3. That is going to be my point of discontinuity that I'm going to try and remove. I can't remove the point of discontinuity caused by the vertical asymptote. That is an infinite discontinuity. But a whole discontinuity, I can remove that. So I'm going to do a little bit of exploration on the calculator around where x equals 3. And I might do it looking at the graph. I might press the trace button. And the trace button gives me a little flashing thingy there. I'll try and point to it here, right over there somewhere. I hope you can see it. And that little flashing, let's get rid of that finger. A little flashing thingy, I'm going to move it along the function by pressing my right arrow. And I'm looking at my x values. I'm at 1.48, 1.70, 1.91, 1.21. I'm getting closer to 3, which is where I think I have the problem. 2.76, 2.97. I'm going to write this one down because it's very close to 3. So at x equals let's call it 2.98, y equals 3.31. I'm going to click it again. Now I've gone past 3, so at x equals 3.19, my y equals 3.51. So I know that my limit as x approaches that hole is somewhere between these two values. There's a hole at x equals 3, and the y values to the left of it is 3.31, and to the right of it is 3.51. So it has to be in between those two values. Well, let's go to my table and see if I can get it even any closer. So I'm going to go second, table set. I'd like my table to start at 3, which is where I know the point of discontinuity is going to be. And since I'm trying to come in at a single point from the left and the right, I usually set my delta table at 0.01. And now I'm going to go second table. And I see that, well, at 2.99, I'm going to extend this a little bit. According to my table, at x equal 2.99, my y is equal to 3.32. And at x equal 3.01, my y value is 3.34. Well, it seems to me as if my y value, my limit as I'm approaching 3, is going to be 3.33. But that is a decimal approximation, but it's something that we can start with and use right now. I want to see if I can find the point of discontinuity algebraically. Now I know the point of discontinuity is going to be at x equals 3. But I want to find out what is the limit there, because I want to be able to fill that hole. I want to be able to fill that hole with the right point. So I factored my denominator here, and according to this, I have an undefined value at -3, which fits what my graph shows, this vertical asymptote. But it also says that I have a hole here at +3, because it has to be undefined, but it's not a vertical asymptote. The only choice left is for it to be a hole. Well, a hole arises when I can cancel a factor from the numerator and the denominator. So if I have a hole at x minus 3, it must mean that x minus 3 is a factor of my numerator. Well, how do I find out if it's a factor of my numerator? I'm going to use synthetic division to find that out. So synthetic division says, if in fact I have a linear factor of a polynomial, I can take the coefficients of the polynomial. So x cubed, my coefficient is 1. I have to have a coefficient for every single power of x. So since there is no x squared there, my coefficient is 0. My power of 1 is -7. And my power of 0, my constant, is -6. And if I use synthetic division with x equals 3, then I should find out whether or not this is indeed a factor of this polynomial. So let's use synthetic division. I'm going to bring the 1 down. 3 times 1 is 3. I add those two together. They add up to 3. 3 times 3 is 9. I add these two together. I get +2. 3 times 2 is 6. I add these two together. I get 0. The fact that I get 0 as a remainder shows that x minus 3 is a factor of my numerator. And it tells me what the remainder is. So I know that this polynomial here, this one right here, my numerator, can now be rewritten as x minus 3 times x squared, that's 1x squared, plus 3x plus 2. That is how I write my new numerator. And I divide that by the denominator, which was x plus 3, x minus 3, x plus 3, x minus 3. And I find that my function, which was this, I can now write in lowest form by crossing that out. And I can now write this as x squared plus 3x plus 2 divided by x plus 3. This is not identical to our original function. Our original function was a cubic divided by a quadratic. This is not. Our original function had a hole at x equals 3, but this one does not. But this is going to allow us now to find the limit as x approaches 3. Because I can take a limit as x approaches 3 of this function using substitution. Because I have a polynomial as a numerator, I have a polynomial as a denominator, and as x approaches 3, I'm not running into the problem of getting 0 in my denominator. So let's see what happens if we do substitution now. So I would have 3 squared plus 3 times 3, let's put that 3 in parentheses, that's our limit as x approaches 3, plus 2, divided by 3 plus 3. So that is equal to 9 plus 9 plus 2 over 6, which is equal to 20 over 6, which is equal to, amazingly enough, 10/3. The decimal approximation for 10/3, 3.333, which is exactly what we had approximated using our table and our calculator earlier. So how do I rewrite this function now to get rid of this particular, remove this discontinuity? Well, what I'm going to do is this. I'm going to turn this function into a piecewise function. So I'm going to go f of x is equal to this top part right here, and it is equal to 10/3, where x is equal to 3. So I removed that discontinuity by putting in the exact value needed, the exact y value, to fill the hole in that graph.